Okay, so what I want to do today is I want to give you a little push on the homework, on some things, and talk a little bit, which is going to involve talking more about derivatives. Then I want to start getting into the idea of accelerations and also some qualitative graphs, stuff like that. Okay, so I want to say more about the formal definition of a derivative. This formal definition is really important, especially if any of you are, let's say, an engineer. You're going to need this formal derivation when you do any type of numerical work. So you're going to use this here. If you're a mathematician, then not in math, then obviously then you need it. You use this formal definition quite a bit in life. Okay, so f versus x. Here's a function. Let's say here's the point x. Here's the point f of x. Now you tell me, if I put you back in Calc 1, what would you now say is a formal definition of derivative? What do you do to that picture now? And that's close. Just be using yes. Okay, you're not going to call H, you're going to call it delta x, but you're completely correct. Okay. Almost perfect. Just put a minus sign in there and you're going. Okay. So what are we going to do? We're going to come over here at some point here. This is going to be at the point x plus delta x. The mathematicians almost always call this h. I like using delta because delta always kind of refers to a small quantity. So to me, it just makes a little more sense. And then this point here is an f of x plus delta x. If you look over here, this part right here, this is our rise. This is our rise. And you're going to call that delta f. And that rise is going to be this value minus this value. And this right here is our run. That's your delta x. So the slope of that secant, again, if I have a secant here like that, it's going to be rise over run. So the slope of the secant is this f of x plus delta x minus f of x all over delta x. Does that part make sense? Questions with that? Then formally, if we want the derivative, what is it going to be? You take this delta x as it gets smaller and smaller and smaller, like this. And so what's going to happen? The slope of the secant ends up becoming what? The slope of the... Let me make this look a little more secant-y. I'm just going to make this look a little more secant. So if I let this delta x become smaller and smaller and smaller, so what happens? I'm going to take that delta x, it becomes smaller, that moves over to here. I have that point. Now I have this slope. It gets smaller. At this point, now I have this slope. Bit by bit, what does this slope become? It becomes the slope of the function. One more word in front of that. Slope of the okay, not quite yet. Slope of the tangent. So what you're going to do, if you take the limit, as this delta x goes to 0, this right here. That's the formal definition of the derivative. And this is really the slope of the tangent line at x. Does that make sense? Questions of that? Now, I do theoretical physics. I like to know where things come from, and I want you to have a better understanding of where things come from. So on the homework, does anyone have a copy of the homework with them? There's two problems. Do you have it in front? So there's two problems here. I'm going to give you a little push on. Okay. On questions number 3 and number 4 here, what I'm gonna have you do is I want you to use that formal definition here to actually calculate the derivatives. So I can do a variation on one and then I can give you a little push on that one. So I have you actually formally calculate the derivative of the cosine. I'm gonna do the sine for you. So, homework 1, okay, you will use this definition to derive the derivatives of f equals cosine of x, and f equals a constant a times x to the n. So you're going to use this formal definition to derive the derivative of each of these here. Okay, and what I want to do is, I'm not going to do this one for you, but I'm going to do the sine, and you're going to do a variation on that. I'm going to give you a little kickstart in this guy here. Okay? Again, because I want you to know where everything is coming from in life. Okay, so let's do this. So how? So here's an example. How can we use form? Was that on the board? So how can we use the formal definition of a derivative to derive d sine of x dx? I'm going to put theta in here. I like thetas. It seems like when you have a sine or a cosine, you should have a theta, not an x. Okay. Oh, what is this equal to? Derivative of sine is a cosine. Okay. So how can I use this right here? Put this right here. Okay, that makes sense. First of all, we need a little background first. So first, 2 points. Okay, right triangle. This is the right triangle. This side is the opposite. This side is the adjacent. This side is the hypotenuse. Okay, so a sine theta is by definition, what is it? Opposite over hypotenuse. Okay, this is something you're going to use for the, if you take this course, it's going to be used constantly. If you're in any type of engineer, you just have to have that. That's just your bread and butter. You have to have that completely burned into your synapses, so you can just write it down without thinking anything about it. Just out of curiosity, why do we only deal with right triangles with this? What's special about a right triangle? Maybe you have some weird triangle like this. What's wrong with that triangle?
I agree with you.
Well, sure. Something else. Do I want my definition of the sine of an angle to vary on the size of my triangle? Or how it looks? No. So you can see what happens here if I make this bigger. Okay. Or bigger. What's going to happen to the ratios here in each of those cases? That ratio is going to stay the same. And if you have some other weird, if you don't specify the type of triangle you're dealing with, let's say somebody has some triangle like this, and somebody else has some triangle like, like that, somebody else has one like this, you're going to get all weird results here. But if you specify just the same type of triangle, no matter what, then the ratios will always be the same. So it's independent of my triangle. of the size. Okay, then tell me about my buddy cosine. Adjacent over hypotenuse. Since we're at it, let's get our friend tangent theta. Opposite over adjacent. Okay, so this is this one. We're going to need both of these here. Now the other point. Okay. What is the formal definition of radians? Right, you can measure angles in terms of degrees. You can also measure it in terms of radians. What is the formal definition of the angle in terms of radians? Radians. Good thing to know. Okay, here's a circle. Has a radius r here like this. Okay. So this is r. Call this here angle of theta. Kind of looks like a Pokemon thing, doesn't it? Which is an incomprehensible game. When my daughter was little and she wanted to play Pokemon, I started looking at the rules. I went, I'm sorry, Pumpkin. Daddy's not smart enough to play this. And then we did something else. It's incomprehensible. Like just FYI. Okay. So, what do we call that part there? That is the arc length, and it's always S. So this is our S. This is our arc length. Okay. Theta in radians. Uh-oh. Yeah, I'm sorry. Theta in radians is by definition what? We're going to use this expression a lot.
Are you looking for like the conversion?
We're going to get the conversion out of this. So how do we formally define the angle in terms of radians? It is the arc length here, S, divided by the radius r. Okay, that's the formal definition of this thing. That makes sense? Now, what is the formal how does the conversion go from radians to degrees? 360 degrees is how many radians? 2 pi radians. How come? Why are there 2 pi radians in a circle? From this, you now know exactly why. Okay, let's draw this. Okay, so what do we have here? Circle. Here's R. This. If I go all the way around here, let's say that's my S. So that means that this whole angle here is theta. So let's use our definition here. It's the arc length over the radius. So what is the whole distance around a circle? Well, that's the angles. What's the distance? 2 pi r. This circumference is 2 pi r. So that's my S divided by r. Those crazy r's cancel, and you have 2 pi radians. Okay. That's why there are 2 pi radians in a circle. Okay. Now let me ask you a trick question. Why are there 360 degrees in a circle? It's a trick question. You have to blame the Babylonians. Okay. The Babylonians, okay, they did not have base 10. They had base 1. Base 60. When we work it out, if you have a base 60, you get 360 degrees in a circle. So you could say, why on earth would a society, and actually the Babylonians were amazing, why on earth would they have base 60? This actually, I'll give you this is brilliant. What do you want to do with math in the ancient world? Well, I make you farmers and shepherds and artisans back in, 2000 BC. And what are you going to use math? Probably business and really practical stuff. So let's say you have a whole bunch of grain here. And what might you want to do with that big pile of grain? Break it up in equal piles. Okay. If you have base 60, a lot of things divide into 60. So you can actually take your big pile of grain and break it up into a lot of variations on here. 5 goes into it, 12, 3, 2. A lot of things go into 60. You can divide a lot of things evenly. So just from a practical point of view, if you have to divide something up equally, base 60, if you don't have computers with a lot of advanced mathematics, is a really great thing to use. That's brilliant, utterly brilliant. Okay, that makes sense. Now, how's this connected with this idea here? It turns out it's not. No, here's how it's connected. Let's say I have something like this. Let's say this following. What is the sine or cosine of a small angle? So here's going to be my tiny little triangle like this. And I'm going to call this angle here, since it's a tiny angle. If it's a tiny angle, what might I call the angle? What's our new fancy way of writing tiny angles? Okay, theta, what might I put in front of it if it's tiny? A d. If I want a little bit bigger, I'd call it a delta. So it's either a d theta or a delta theta. Take your pick. I can call it delta theta for no good reason right now. Okay. So I can call that tiny little angle here delta theta. Okay. And here's my opposite side. Here's my adjacent. Here's my hypotenuse. And here's this right here. All right. So what is the sine then of this right here? Sine of theta is what? It's just going to be the opposite. Oh, I'm sorry. The sine of delta theta is going to be the opposite over the adjacent. Frequently called the hypotenuse, because that turns out that hypotenuse starts with the letter H. Okay. And adjacent starts with the letter A. So we're in the setting with H, we'll call it hypotenuse. And then the cosine of delta theta is going to be your adjacent over the hypotenuse. Okay. Now, let's look at the cosine. If that delta theta gets small, if it keeps on getting smaller, what does this look like? This starts looking like that. Here's your adjacent. Here's your opposite, and here's your hypotenuse. How does the adjacent and the hypotenuse start comparing? If that angle gets smaller and smaller and smaller and smaller and smaller.
They almost become the same.
They almost become the same thing. So what might be a good thing to call this then? That's going to go to 1. So what's going to happen here is that in the limit, that this delta theta goes to 0, your cosine of delta theta is going to go to 1. Does that make sense? Now we have to be a little more careful on the sine. So first of all, if you're to do the same thing with the sine here, what do you think this is going to become? And you're right, but we're going to tinker with the sine. So if it goes smaller, what is going to be the sine of a really small angle then? What's happening to this opposite side as this triangle gets smaller and smaller and smaller and smaller and smaller? It's going to 0. And so this right here is going to go to 0. So if I were to say the limit, delta theta going to 0, the sine of delta theta, that's going to go to 0. Now, it turns out we're going to be a little more fussy on that. And that's true. But you're going to see why. We're going to do something a little more subtle there. I want to give you another way to write this down here. It's not going to be quite in the limit part, but as we're making it smaller and smaller and smaller. You're going to then see why we need this. So, as delta theta becomes small, okay, we can show that sine of delta theta is approximately delta theta. And then if your delta theta goes to 0, then you get this. So what I want to do is show you why the sine of delta theta is pretty much this. Okay. I'll give you a hint. Make sure you didn't know it. Let's draw this. So proof. So here's my little triangle like this. Here's my delta theta. Here's my opposite. Here's my adjacent. And here's my hypotenuse. We know that the sine of delta theta is always your opposite over hypotenuse. Okay? This hypotenuse here, I'll just call it like this. Okay? But if this gets smaller and smaller and smaller and smaller, so here's my A, here's my H, here's my delta theta. I'm sorry. My opposite. I can also compare this to a circle. Oh, let's make it look a little more circly. That kind of sad, but it'll work. Okay. What is this going to become then? This is going to start looking like my arc length. What's my hypotenuse going to look like? My adjacent or the radius. And here's my little delta theta. Okay. So what do I know about the definition of the angle? The angle is what, by definition? In terms of radius, it is the arc length S over the radius. But my arc length S is my opposite, and my radius is now my hypotenuse. Hey, does opposite over hypotenuse have another name? Sine. Okay. Okay, so this is going to become my sine of delta theta. Okay. That makes sense? Now, is everyone here in Calc 2, or has everyone here had Calc 2? No. Okay, then I won't mention something else. There's another way to do this, which is amazing, but we're not there yet. Okay, now let's use that. So just keep that in mind. Okay, well, let's use the formal definition. Let's go through and do this. Okay, so proof that derivative of sine of x dx is cosine of x. I said theta, didn't I? Theta. Okay. There. Okay, let's go through and do the formal definition. So what is the formal definition of the derivative? Remember the formal definition of a derivative is the limit as delta x goes to 0 of what? F evaluated at the point x plus delta x. Keep going. Minus f of x all over delta x. So let's use this in this case here. And in this case, what is my function? Sine of theta. So here I'm going to take the limit as delta theta goes to 0 of here's my function here f. This is my f. This theta here is acting like my x. Okay, so I'm going to have sine evaluated where? Exactly. Theta plus delta theta. So this term here, this is like my f of x plus delta x. Minus what? Sine of theta. Right, so this is my f of x. Now I have to divide that by change in theta. So this is like my delta x. Okay. Now I'm going to clap my hands and you're magically going to become, go back to 11th grade. I think it's in 11th grade you do this. You see sine of two angles like this being added. What do you think? You think of the sine of A plus B. Okay. And let me give you the sense of how the mighty have fallen. At one time in New York State, my family's been in this area forever. At one time in New York State, you had to actually be able to derive those trig functions on the regions. But now they've gotten rid of all this and made the regions now exempt idiotic, but we've somehow raised standards. Got it. Okay. So now we have the sine of a plus b. What does that equal? Sine, sine a cosine b plus
I don't.
sine cosine. Good. Okay. In this case here, a is what?
Theta.
Theta, or b is delta theta. So let's use this. So if this limit, this delta theta goes to 0. Of here. So tell me what to put in the top here. If I use this here, tell me what to write. Sine of theta. Cosine. Delta. Theta. Plus sine of delta theta. Cosine of theta. Okay. Okay. Minus my buddy here. All of delta theta. You say, wow, that looks just like cosine of theta. It does. Okay, now let's go through and do it. Now, what do we have to do? We have to do this limit here. So tell me about this. What happens when you take the cosine of an angle getting smaller and smaller and smaller? What did we just state that happens? It goes to 1. Okay. So as we take the limit, as this goes to 0 here, this goes to 1. So this is going to become the sine of theta. Okay. That goes to 1. Okay. Plus. Now, we have the cosine of theta here. Now, what did we just state about the sine of a tiny angle here? Ultimately, it will. But what happens is as we inch along there, don't go to the 0 yet. It becomes basically this angle here. It's going to ultimately go to 0. Well, we can't do that yet. Okay, here. So this is this guy. Then minus sine of theta. All over delta theta. What great thing happens? That is going to cancel this. And now we have delta theta, cosine of theta, over delta theta. What wonderful thing happens? Delta thetas go out, and this is our cosine of theta. So, beautiful proof. On your first test, there won't be more than like 13 or 14 of these. I'm kidding. There won't be any. Okay. I'd also like to sing while you take your test because that'll help you concentrate. So I can't really sing well, but that never stops me from. And everything I sing will go to the tune of Gilligan's Island. Okay, that'll help you concentrate. Okay, so.
Your request song.
No, it turns out that that's as long as it goes to the tune of Gilligan's Island. Okay. Questions with that? Okay, I want to give you a little push on it. So what you're going to do, you're going to repeat this argument, but it's going to be modified, but you're going to have the cosine in here. Okay? But it's going to be the same type of result. Any questions with that? Again, I like people to know where things come from. I can't do this for all of them, but we're going to use sines and cosines so much, I want you to do it. Now the other one, I'll give you a push on number 4. So number 4, I want you to prove that the derivative of some constant times x to the n, a is a constant, is the constant times n x to the n minus 1, using the formal theorem. Okay. So let's go through and see how you do that. And again, I'm not going to do it for you. I'm just going to give you a push. Okay. So let's go through and do this. So if I wanted the formal proof of this guy here, This is gonna be the limit. This delta x goes to 0. And this right here, this is my function. That's my f. So what goes in there? So tell me what you write. Okay, the constant comes along to the right. Remember, we have this f of x plus delta x minus f of x all over delta x. So how do I write? I want this to be my function here. What does that look like?
A actually.
A times x plus delta x all raised to the n power. That's what this is here. Does that make sense? Okay. Then you have to subtract the original function. It's ax to the n. So here's my original function. And this all gets divided by delta x. So you're going to start with that. And I give you a hint. If you look at that problem, I tell you something. What do I tell you?
Plus delta x to the n.
Yeah, I tell you. Okay, so you will use the fact that if you have x plus delta x to the n power. Okay, first of all, what does that mean?
Raised to some number.
Yeah, you have x plus delta x, and how many of those do you have multiplying by each other? N of them. Okay. But if you work this out, so in other words, what is this guy? This is really x plus delta x, x plus delta x. You have n of these guys here. If you multiply these all out, what do you get? You get x to the n plus n times x to the n minus 1 delta x plus n times n minus 1, 2, x to the n minus 2 delta x squared. That does that all the way to the last one, which is delta x to the n. Okay. You're going to take this mess here, put it in here. Remember, you're still multiplying by a. And all you have to do is be careful with the mathematics. Okay. Work all the mathematics before you take that limit. I mean, before you put in the delta x goes to 0. That make sense? Again, work on that. Work on it with your buddies, group. I don't care what. Come by, show me what you have. I want to see what you've done. I don't care if it's crap. I mean, I can look at this and go, oh my, that's just insane. But that's perfectly fine. I mean, you're learning this. I would, if everything's perfect that you're showing me, then frankly, why are you in the class? You should be in the next class. So I'm not expecting it to look perfect or even great. I don't care about that. But I want to see blood. Okay, I want to look at your paper and say, I see a sign that you basically have blood. I want to see blood, skin, bones, sweat on that paper. It doesn't have to be right after that. I want to see something where you've given an effort to it. Otherwise, it doesn't really help to come by for help. Okay. And again, if you're scared to come by for help, you can bring your buddies. That's fine, or a group, and that'll also work. Okay. Questions with that? Make sense? Okay. I want to talk about doing some of these graphs, some of these things qualitatively. I want to talk about how can you draw a qualitative V versus T graph from X versus T. Let's set this up and then I'll explain. So let's say I have an X versus T graph like this. And let's say it happens to look like this. I'm just making it up. So here's some object. The position versus time is like that for no good reason. And I want a qualitative V versus T. What does qualitative mean? I didn't ask for quantitative. I asked for qualitative.
The numbers don't really matter.
Yeah, it's going to be a sketch that's kind of correct as long if you look at it, you know, if you wanted to get like numerical values from it, it's not going to work at all. This is going to be, it'll look more or less right, but it's not going to have necessarily the exact, you know, mathematical form correctly on this. Okay, so it's a sketch. Okay, that's what I'm asking for. So how would that look? So let's go through and do this. For the rest of your life, well, at least meaning in this course, okay? I'm not going to call you up when you're 35 and say, so do you remember in August 28, 2024, I said about the velocity always equaling something, what was it? You know, I'm not going to do that. But what did we say the velocity is going to be for the rest of your life, meaning in this course? Velocity is always, always, always. Not necessarily. It's your dx over dt. Okay, so your velocity is dx dt. Again, what does dx mean? Dx is just it's like delta x, but it is remarkably small. Okay, what would a mathematician call the dx? They are called, good math word, infinitesimals. So the dx all by itself or the dt all by itself is called an infinitesimal. Okay. So what does this mean? It means that you have an object going like that. It means it moves some tiny little distance. That's the dx. And how long does it take to move that tiny little distance? That tiny little time dt. And that ratio is your actual velocity. But we also know that this is what? This is nothing but, the derivative is nothing but the slope of the tangent line at a point. So this is nothing but the slope of the tangent line at the time t. Okay, so what we have to do, we have to draw a series of dots. Okay, we're going to look at this time, we're going to look at this time, this time, this time, this time, this time. And at each of those times, you're going to draw the slope and then graph it down here. Now, when you see something like this, and you're going to see this a lot, and if you're an engineer, you're going to do this all the time. You want to do the easy points here first. So where would be the really, really easy point? And it's going to really anchor this graph down here. It's going to be basically where the object is not moving. The zeros. So where would the zeros here occur in this graph? Where does the tangent line have no slope?
No.
At the maximum here. So this max here, right? I draw this max. I draw my tangent line here like this. That's my slope. This has zero slope. So what does that mean about the velocity? Yeah. So this is at this time here. So at this time here, at that time here, I have no velocity. So at the same time here, I'm going to carry down this line here like that. I put a zero there. And if this thing went like this, you basically all the maximums and minimums, you put all those zeros there. We'll do one like that in a second. Okay? That makes sense. Just tell me in terms of words, why that makes perfect sense that object isn't moving there. How does the position vary from here to there to there to here to here to here to here? How's that position varying along there?
Not really.
There's almost no variation in the position, right? When you're toward this peak here, or same thing with the minimum, as you kind of march along here, like the points around here, here, that x is barely changing. If that x is barely changing, that dx is zero. That's why that object isn't moving. Not too hard. Okay, once you get all the zeros anchored in here, you start on this end and you march to this end here. Okay, so let's draw it right here. Here's my point. What is my slope here? Positive, negative, or zero? Yeah, if I draw my little slope here, it's like this. That's my tangent line to that point here. So that means this is at t equals zero. So at t equals zero, I put some positive value. I should have put it here, 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 here. Where should I put it? If it's a qualitative graph. It doesn't matter as long as it's positive. Okay, so I'm gonna say here, that looks like a great point. Somebody else might have it here, fine. It doesn't, somebody might have it way up here. Okay, great. Okay, don't put it like here. Okay, because that's gonna be, you're not gonna see what's going on. Put it so you can see where something's going on. It's qualitative. Okay, now we're gonna march over to this point here. So at this time here, I'll look at that slope there. What is that slope gonna be?
Positive,
Positive, how does the slope here compare to the slope here?
it's less.
It's less, right? If I draw it, it's like this. So I come down to this point here. And where should I put then that slope?
Between the 2 points, yeah.
Yeah, somewhere here like this. Okay, now the way I've drawn it, it looks like a straight line. And maybe it is. Now maybe somebody's gonna have it lower, so it's gonna be a little more curved. Again, it's qualitative, it doesn't matter how you do it. Okay, if you had a mathematical form, you can do it. Okay, now let's go over here. So this will give us this far. Now let's say I'm here. What's the slope look like there? It's negative. Okay, so I'm gonna have a little negative over here. So how that means at this point here, what am I gonna do? I'm gonna put a little t. Now would it go way down here? Probably not, because I look at this slope and that slope and they're kind of comparable. So I'm gonna kind of have some negative value. I'm gonna put it there for no good reason. Okay. I'll put in one more point, call it good. If I go here, what about the slope at that point?
Greater, still negative.
Yes, more negative. Okay, so I come down here at this point, I come down here, I get this. So a qualitative graph is going to be something like, no, let's have to go through the points. It's going to be something like that. That makes sense? You're going to be seeing a lot of those this guy. Can I put numbers on this guy?
You would want to.
Yeah, you get, without having the functional form here, without knowing what this function is, there's no way you can get numbers from this. Again, it's a qualitative graph. Okay. Now tell me what this is actually. This is one of these things you don't need calculus for. Let's say I were to give, let's say I go to kindergarten. And I tell pull up some random kid and say, hey, random kid. Okay. There's a car. This is how the car is moving. Okay. What would that kid say? You look at this part here, how the distance is getting greater. What would he say? Oh, it's going to the right, right? Because the distance is increasing. So we have this positive velocity. Well, probably wouldn't use the word velocity, but that's fine. But what would happen is you're going to this point here. You're going to be slowing up, slowing up, slowing up here. And then what's going to happen? As you go this point here, the distance here is actually getting smaller and smaller and smaller, right? It's decreasing, meaning it's going to the left. So you could have figured that out without fancy calculus, just by looking at the graph and thinking. Okay, does that make sense? Questions? Okay, let's start something and then we can start pulling a lot of the ideas together. Okay, so we're not done with this. We're gonna come back and revisit it, but that's what we need right now for this. Okay, let's go back to our little picture with 1D kinematics and add some more to it. Let's go back to our graph here. Here's a wall. I'm going to call this X1. This would be T1. Let's say the car has some velocity here. I'm going to call that V1 right here. Right down the road, this over to here. This is sometime T2. This is X2. This is going to have some velocity in V2. And what I can do is I can make a graph of V versus T just like we did before. Okay. Actually, let's do something else. I need to find something called the average acceleration. We call this A bar or A average. Yes. And it is going to be by definition. Okay. Maybe you've seen this in high school, maybe you haven't. How do you think we define acceleration? What?
Meters per second squared.
They're gonna be the units for it, but what's the formal definition of that?
Change.
Yeah, it's gonna be the change in velocity. So in other words, we're gonna take this velocity here minus this velocity. So it's the change, it's gonna be V2 minus V1 over how long it takes to change. So this would be T2 minus T1. So what this is really delta V over delta T. So we get this. So our average velocity is this guy here. Okay, that makes sense? So let's get the unit for this. Okay, what do we measure delta V in? Okay, let's do the MKS ones. Delta V is measured in terms of meters per second. Change in time is second. So if you want, you could say it's meter per second per second. That's perfectly fine. No one ever does that. Okay. Instead, what you have, since you have 2 seconds in the bottom, this is really a meter per second squared. Okay. That makes sense? Okay, what would we have then for CGS? Centimeters per second squared. Okay. And then for English, yeah, we're gonna have feet per second. Yes. Okay. That makes sense. So let's look at a graph of this. Okay. Physicists also, physicists never throw things away. What you do is you learn a trick and you beat that trick to death. And so a lot of the ideas you learn them, and then basically you just beat it to death. Again, to know physics, you have to know remarkably little. Okay. There is a catch though. The remarkable little amount of information you need to know, you have to know it really, really well. Okay, there's a catch. Okay. Let's make a graph. Here's our R. This is V. This is versus T. And let's say it looks like this. And here's T1. This is V1. How am I doing on time? Get this one point in the call. That's T2. And this is V2. Hey, graphically, tell me, what is the average acceleration graphically?
Slope of the tangent.
Change the one word there. The slope of the secant. Okay. So the average velocity here, if I were to do this, okay, this is my change in V. This is V2 minus V1. Here's my change in T. T2 minus T1. So if I had my delta V over delta T, this is going to be the slope of the secant. This right here, that's my secant. That, and this right here, that's my average acceleration. Hey, what do you think we're going to do on Friday?
That. More of that.
More? I want to know, this is fine for the average velocity. So maybe, again, we're driving to Cornell. Maybe this is my speed here at one point, and here's my speed later on. But I want to know exactly what my acceleration is at a point. Hey, what am I going to do? Oh, I also teach people how to speak Scooby-Doo. So to speak Scooby-Doo, you basically put R's in front of things. So in terms of Scooby-Doo, this would be ring, ring, Raggy. So ring, ring would be same thing. Raggy would be Shaggy. So ring, ring, Raggy. Same thing, Shaggy. What does that mean? We're going to take this quantity here, and what are we going to do with our delta T? Make it smaller and smaller and smaller, and that's going to ultimately be the actual acceleration of it. Okay, we do that on Friday. I'm going to set this all up again, same as before. You're going to be bored by it, but that's fine because you get kind of frustrated and bored, like we know this. I want that to occur because that means it's kind of setting into your head, rock solid. Have a great day. What? I do, yes. If you maybe not.